Hello, everyone. We're here today with Xavier Bouthillier. He'll be telling us about hyperparameter optimization using Dask with Orion. And he's joining us from the University de Montreal, where he's a research developer in the Innovations Development and Technology team. And he's the leading the development of the hyperparameter optimization framework called Orion. Thank you.
Thank you. So I shall begin now, or right?
Please.
Okay.
Please.
Sorry.
Yeah, thank you.
Yeah. Thank you. Oops. Share my screen. All good? Yes?
Yes.
I'll assume yes. Okay.
Yes.
So hi, everyone. Xavier Bouthillier is a PhD student and also a research developer at Mila, actually, but we are associated to UDM and 3 other universities. And I'll be presenting you, hyperparameter optimization or more generally black box optimization using Dask with Orion. So first of all, what is Orion? It's an open source Python library for asynchronous black box optimization. It is being developed at Mila since 2018 by the IDT team, so Innovation Development and Technology team at Mila. Mila is a research institute that is born from the partnership of different professors at 4 different universities in Montreal. It rallies more than 500 students, researchers now, mostly master and PhD students. And the role of the IDT team is to support the researchers with the computational infrastructure. So we have our own cluster at Mila and also have access to clusters at Compute Canada, Compute Quebec. And also to develop new tools to help them. And one of the examples is Orion that I'll be presenting today. And since a bit more than a year now, we've been collaborating with IBM on the development of Orion, and Yugang, who is the leader of the team at IBM that is collaborating with us. So today's short agenda, I will first introduce the black box optimization for those that are not familiar with it. And then I will give you a short introduction to Orion and an example of how to use it, and then an example of usage with Dask based on the integration we've done. So first of all, what is black box optimization? We have a black box process. So that means we only know what is coming in and what is coming out, but we don't know what exactly is going on inside of the black box. And that means when we're doing the optimization, we have no domain knowledge. We can only adjust the values that are coming in to optimize what is coming out. So to give an example that is close to machine learning or artificial intelligence, let's say we have a robot here that is able to learn to do a task. So let's say it's going to serve this glass of water here. And let's say we don't know how the robot is trained. Okay, the only thing we can do is to configure the robot so that it can learn. So the training of the robot itself is happening inside the black box. And we only configure the robot with the knobs here. And then the robot is trained in some way. We don't know how. It is evaluated, and then we see if the robot was able to solve the task or not. Perhaps not. And then we go back, we readjust the knobs, and we go again through this process, and we try to optimize the learning behavior of the robot. Okay. So this is the idea of black box optimization. But it's really a black box. So it could be basically anything. It could be, for example, optimizing a cookie recipe. And this is actually something that was done by Google in their paper about their black box optimization tool, Xavier. They really optimize the cookie recipe, bake the cookies, evaluate the cookies, and go iteratively like this. Okay, so it's very general thing. To do the black box optimization, we need first to define what is the search space. So what are the correct values that can be used, but also what are the relevant values that could be used through this black box process. So for instance, it could be the amount of flour and the amount of chocolate chips that are being used in the recipe to bake this cookie. And when you have these optimization, the search space, now you need to define or decide which optimization methods to use. I'll just go quickly over different families that are that you could use. Okay. First example is very simple ones, the grid search or random search. So you would basically just equally divide the search space or the amount of flour and chocolate chips or you would just randomly sample values of a different amount of flour and chocolate chips, and that would be how you decide which recipes to try. So these methods are very simple but very inefficient because you're not looking at the actual objective, so the outcome of the black box process, to try to guide the different recipe you would try. You need to literally cook all the recipes, try them, and then pick the best one. Another family of algorithms is the evolutionary algorithms. In this case, we would start like the random search with random recipes. Okay, then we bake all of these recipes, but that would be a smaller subset than if you do random search. And now you cook these recipes. Okay, you evaluate the cookies, and then you compare them. And now you would have the worst recipes lose the competition, let's say. So you remove these recipes, they're not interesting. And obviously that would be those with less chocolate chips to begin with, and those with maybe too much flour, okay? And then you mutate the best recipe. So you just slightly nudge the values for the flour and chocolate chips, and that gives you new recipes to try. And you do this with all the best ones. And you do this iteratively many times. So again, you would cook all these recipes, and you would have the results that you evaluate, and you drop the worst ones and mutate the best ones, and you iterate like this until you either exhausted your cooking budget, or you kind of converge, let's say. Okay, and finally, last family of optimization method is the model-based algorithms. So, for instance, Bayesian optimization, for those familiar with this. Okay, so here we have a red curve that would represent, in an ideal world, the average humanness of a recipe in the population. Okay, so that's like that's the true value that we are trying to find out with our model when we're optimizing. Okay, so we have on the left let's say the healthy cookie with just a low amount of chocolate chips, and then there's this valley of disillusion where there's not enough chocolate chips and it's just disappointing. And finally, we have the good, fat, and sweet cookies that are the best ones in general. Okay, and now we want to find this. So we have a mathematical model, like a Gaussian process, for those familiar with it, that we will fit on some data to try to predict the humanness of the recipe. So first we randomly sample a couple of recipes. So here we just have the chocolate chip axis and 3 different recipes here that we sample. We fit our model on this, and then we use this model to try to predict how good a recipe would be for different values, for different amount of chocolate chips. And this is represented here by the green line here. And also we have a measure of the uncertainty of this model represented by the green area here. And now based on this, we compute, say, the usefulness of trying a new recipe, which is represented here in blue. So that means, for instance, this amount of chocolate chips here, it would not be useful to try it again because the model is pretty certain and we know it's a bad value. It's not good recipe. But here, for instance, we have a lot of uncertainty and it seems to predict that that would be a good recipe. So that would be a useful recipe to try. And so we bake these cookie, we evaluate it, we fit the model again, and we do this iteratively, like for the evolution algorithms, until, again, either we exhausted the cooking budget or we converged to a good recipe. All right, so that was a quick overview of the different algorithms that you could use for black box optimization. Now I'm going to talk about Orion. So for the design principles of Orion, there's many reasons that so that we decided to build Orion 3 years ago now. But I will focus on those that are relevant to Dask. And so it's the reasons that turn around our environment, computational environment, so the HPC. And we had issues with the other libraries at the time and the HPC for a couple of different reasons, and I'm going to outline here. So first one, there was no nodes for persistent processes. So forget about having a database on the cluster itself. It needs to be hosted externally. But also for the master process that would execute this optimization algorithm while the workers are doing the hard work, It cannot be on a persistent process on the HPC. It cannot be on a login node, for instance. So it needs to be either on the compute node, which is not persistent, or external to the computational infrastructure, to the HPC, which makes it more complicated for the users. Remember, we're at Mila, so we're trying to build tools that are easy to use for the students. And then another issue is in our clusters, we're working with deep learning. So most of the time we're using GPUs, and it turns out that in many cases, it was very often would happen that one of the nodes with the GPU would be faulty, and then all of your jobs in the queue, so we're using Slurm, all the jobs in the Slurm queue would just get smashed on this node, and without knowing, you would lose a day with no jobs running because you're thinking that you have a lot of compute, but actually all the jobs are dead because of this node. So it was really a main issue for us, this instability, and we needed the library to be resilient. Another issue, which is not that major, but is just adding up even more friction for the users, is that on many of the clusters, we had no internet connection in the compute nodes. It's fairly easy to circumvent by just opening SSH tunnels. But again, this is just adding even more friction for the users. And finally, the file system tended to be very slow. It may not be an issue of configuration, but more to bad users. But in any case, it was very slow. So it was important for us to have a solution that would not rely too much on the file system for the I/O. So for instance, we would not want to have a database that is based on the file system. So based on these issues and the others I didn't mention, we developed Orion on a couple of main principles. First one is resiliency. So it is masterless and it is resilient to worker failures. Another one is interoperability. So the example I'm going to give here are based on Python, because I'm using Python with Dask, but actually using the command line API of Orion, you could have a black box that is implemented in any programming language. And also we built it such that if you're configuring your script that you optimize with Orion with some configuration file, it could be any configuration file. As long as it is text-based, it can be used with Orion. And finally, we wanted Orion to be not only a tool for the students to do black box optimization, but also for the researchers that want to develop new black box optimization algorithms to be useful. So we built it such that most components are extendable through plugins. So most importantly, the algorithms themselves, the optimization algorithms themselves, but also the storage backends, and now the executor backends, which is used for the parallelism, like we're doing with Dask, as I just explained shortly. So now I'm going to show you a short example on how to use Orion. So starting with the beginning, it's fairly easy to install, just pip install or using Anaconda. I'll be using the Rosenbrock function as an example. So you have on the right hand side an example visualization of the Rosenbrock function. And we want to minimize the z-axis here. So we want to reach this blue region of global minima by modifying the x and y values. So the function here takes as argument the x and y value that we're going to modify to minimize z. And a and b are just a parameterization of the function. So what you see here is with a equal 1 and b equal 100. And we compute the equation here. So we have z, and now we return the results to Orion. So it's just a list of dictionary. We specify the name of the result, the type, the objective, and the value z. And here for the type, the objective is the main one that the algorithm is minimizing, but you could also return to the algorithm's gradients or constraints or statistics, depending on what the algorithm needs. So now to do the black box optimization, you just import this build experiment function. Then you call the build experiment, give it a name. So here, random Rosenbrock. This is to uniquely identify this experiment in the database. In this example here, we don't need to configure the database because by default, so out of the box, the Orion works with the file-based database. As I just stated earlier, this is not something we want on the HPC. So there's also a MongoDB backend that can be used, but at least you can toy around with Orion out of the box by using this file system-based database or storage system. And then you call experiment.work on the Rosenbrock function for, let's say, a maximum of 20 trials. And so now this is doing the optimization of the Rosenbrock. You could also define which other algorithms you'd like to use, so just giving the name of the algorithm, or you could also define the configuration of the algorithm by giving the different values here that can be used. This is just a short example. So now if we open up the, let's say, the box of the work on function, try to see what is happening in the worker. The first tab in this workflow chart will start here as, so it seems stupid, but first thing that worker will do is look if the experiment is done. And this is because Orion is asynchronous, so maybe there's other workers working at the same time that already completed the experiments before this one started. So we need to start with that. If the experiment is not done, then it will look in the database. Is there a trial available that I can reserve? If there's none, then I will update the status of the algorithm based on what is in the database. I will produce a new trial. So it's a new recipe of cookie to try, and I will register it in the database. And then the worker will just go back to this state here and look, is the experiment done? Let's say there's no other workers, so no, the experiment will not be done. And then is there a trial available? Yes, there would be one because there's no other workers, let's say. So it reserved the trial, execute it, register the results in the database again, and go back to you. And it would just go like this iteratively until it reaches its termination criteria. For instance, max trials 20. And now to distribute Orion, to do the black box optimization in parallel, the only thing you need to do is to just execute your script many times. So you will have, let's say you executed 4 times. You will have 4 different workers, 4 different times you're executing work on. And they will all do the optimization separately, somehow independently. Okay, and it's at the point where they reach this update algo here. So when they get to this box here, what is happening is that they are implicitly synchronizing themselves with all the other workers, because the algorithms are all seeded. So all the workers have inside of them somehow a replication of the algorithm, and they're all going through the same stages, the same steps. So when this worker is here and it updates its algorithm, it will update it based on what is available in the database. And this is data that is coming from also the other workers. And so now this worker will be synchronized with what happened in the other workers, and vice versa. When the other workers will reach there, it will get data from all the other workers and get synchronized. And if you have 2 workers doing it at almost the same time, what happens is that they will produce the same trial since the algorithm is seeded. But then there will be a race condition, and the worker that loses the race condition will just roll back and update again the algorithm and do the steps again to produce a new trial. So this is how we handle the asynchronicity, the race conditions with this distributed workflow. Now coming back to the example just before, remember we imported this build experiment called build experiment random Rosenbrock, and then define the space. Oh, I think I went through the space quickly last time. Okay, so we have the space here, X and Y. We have some prior uniform that goes from -5 to 5. And here was the same for X and Y. And now to run this with Dask, the only thing that the user needs to do is just add this context manager here. So with experiment.temp executor, give here the Dask string so that to specify which backend to use and number of workers. And the signature here of this function is basically the same as the Dask client. So you could pass here whatever a Dask client could use, or you could also pass the client itself. And in this case, it would just be the client that is being used. And then you call experiment.workon, and now it will be doing the parallelism with Dask with 4 workers. So going back to the diagram before, now each of these workers are like a Dask task. So the entire iterative loop of a worker is encapsulated in a function that is executed as a task in Dask. So this is pretty simple. And also the execution of a trial here is executed as a task in Dask. So the worker will use the cc'd and rejoin function so that it can yield the resources that can be used within the task itself, and the worker will not be idle, just sitting there as the trial is being executed. Just a bit more interesting example here. So I'm using scikit-learn, and I skipped the import just to keep it shorter. So here, this is the function that we would like to minimize, let's say. We have as arguments the configuration for an SVM or hyperparameters, if you prefer. So we have C, the gamma, the tolerance, and the class weight. And I'll go quickly through this. So we built the dataset digits. This is from scikit-learn, separated in the features and targets. Then we build SVM based on the hyperparameter configuration. Now we use the joblib parallel backend to use Dask to do this cross-validation in parallel. So we have 5 folds in this cross-validation that will be executed in parallel using Dask. Then we compute the average accuracy across this cross-validation, and we convert it into an error rate because Orion is minimizing by default. So we don't want to minimize the accuracy, we want to minimize the error rate. Now, again, we use the build experiment function to build the experiment. Let's say we give it the name of Dask, maximum trials of 200. We have the search space here. So in this case, it spires in a log uniform distribution from, let's say, 10 to the minus 6 to 10 to the power of 6, and similarly for the gamma and tolerance. And here an example of a categorical dimension, which could have a value of none or balanced. And then again, we have the with experiment.temp executor with the Dask backend. In this case, we spawn 10 workers. Oh, so yeah, a small detail here. When you do not pass a client, by default, Orion will start a local cluster with Dask. So here it will spawn 10 workers in the local cluster. And with Orion, we will only start 2 workers. So there will be 8 workers idle waiting for the cross-validation to execute. And also the Dask workers that are executing the Orion iterative loop will yield the resources and also participate in the execution of the cross-validation. So here, I guess everyone is familiar here with the dashboard, Dask dashboard. So just an example of execution, as I just explained before with scikit-learn. So it takes about 30 seconds to run 200 trials with a cross-validation of 5 folds. So that means training about 1,000 SVM on the digits dataset. It's a fairly toyish example, but still, it's I think it's a good start. All right, so you can see now it will slowly reach the end, and now it's done, completed. All right, so just two small examples for the visualization that you could use using Orion with Dask, but it is mainly based on Orion. So we add this experiment object earlier. Now we can call it plot.regret.show, and this will spawn a server for running an HTML using Plotly. So this is an interactive plot. Actually, this is just a snapshot. And you can see, for instance, how quickly it was optimizing. So here, this is the test error rate on the y-axis and the trials by ordering in time on the x-axis. And you can see how quickly the algorithm. So that was an example of TPE, how quickly it managed to optimize and find optimal values here. Another example that is very useful is the partial dependency. This is something you can also find, for instance, in the scikit-optimize. Here on the diagonal, you have let's say you have the different hyperparameters on the different columns here. So we have C, we have the gamma and the tolerance, okay? On the diagonal here, this is the average objective that you get for the different values of a hyperparameter if you vary the other hyperparameters randomly, okay? And this is very useful, so because you can see then that for very high C, that was the most, that was the best values, and similarly for gamma, for the very small values, it was the best values. And you can see that the tolerance didn't add much effect on the results. And you have the pairwise dependency, so gamma tolerance, for instance, and you can see here how it affects. So the lighter, the better the objective, And you can see here the best region. So this is a very useful visualization to assess how good the optimization was, and also how you should do the next one, like if you should change the search space. I don't have time, so I don't know if I'm too quick or too slow. I'll just continue. I have a few slides left.
You have about 5 more minutes.
All right, 5 would be perfect. So I praised before the masterless design in Orion, but there's obviously also issues coming with it, and I'll go through it. One of them is that it complexifies the implementation of the algorithms because of this asynchronicity and the fact that we're trying to make sure that the replication of algorithms are going through the same steps. There's a lot of corner case that we need to handle both at the level of reproducibility and also at the level of the handling of the race conditions. Another issue is that it requires more I/O with the database because since we have the algorithm replicated in the different workers, each time we update the algorithm, we're fetching a large amount of the trials in the experiment. And if we add the algorithm centralized in the master process instead, we would only do it once. So let's say we have n workers, that means we do n times more I/O with the database. In general, in the deep learning, when we're doing our hyperparameter optimization, we're at scales that are not too problematic for this level of I/O. But let's say sometimes we kind of reach the limit. So we'd like to improve this. And finally, another issue is that to handle the race conditions, we heavily rely on the atomicity of the storage operations. For instance, they need to support a read and write operation. Otherwise, it would lead to corrupted data sets. And this is an issue because, for instance, a lot of students at Mila would like to have a storage system that does not support this atomicity, and so far we cannot provide them this storage because it would just lead to a broken database. So it's starting to be an important issue. So that's why we started to look at Dask, and the integration we made now is just the first step. Now we would like to make a transition to a queue-based workflow so that the state of the algorithm is centralized instead. It will become simpler to operate. There will be less asynchronicity to handle. It will be more efficient. There will be less database I/O, and also thanks to Dask, it will support the resiliency for the workers. But the main issues we have that we still need to tackle is that now we would go back to this problem that the master becomes a single point of failure, and we cannot afford this since if we run the master on a compute node, it's likely that the master may die, and then we lose all the process. And that's related to the fact that we need a persistent process. So this is the issues that we still need to tackle in this transition to a queue-based workflow. That's it. We're looking for interns and full-time developers. So if you're interested, just send your CV to jobs@mila.quebec, and we'll be happy to talk to you. Thank you.
Thank you, Xavier. We have a couple of minutes for questions, if anyone has. We can also continue with questions and answers in the Slack channel. Thank you.